Hi everyone, my name's Nashwan Matheen, and I'm going to be talking about whether we need pre-storm surveyed bathymetry to carry out operational forecasting by evaluating representative and synthetic bathymetry alternatives. So coastal hazard early warning systems provide a means for us to predict the impact of extreme storm events along our coastline ahead of time so that effective mitigation measures can be undertaken to reduce the consequences of these events. These models generally incorporate the use of a coastal numerical model within their workflow to simulate the nearshore morphodynamics and from that predict the coastal change associated with the impeding event. These models require nearshore surf zone bathymetry as a key input, but carrying out pre-storm surveys at short notice within the high energy surf zone can be quite a challenging task. So when carrying out operational forecasting, we have to consider alternative ways in which we can provide bathymetry to the coastal models. So this can include irregularly updating the bathymetry in the models whenever new surveys are carried out, or using remotely sensed bathymetry like CBATHY or satellite-derived bathymetry, or synthetic bathymetry like an equilibrium profile or bathymetry representative of the site. The approach of using synthetic and representative bathymetries requires the least effort because it doesn't require continuous monitoring or continuous surveys to be carried out at a site, and it doesn't require the installation of costly remote sensing infrastructure. But we don't really have an idea of how accurate the erosion estimates are the erosion estimates we obtain are if we use the synthetic and representative bathymetries. So the aim of this research is to use the XBeach coastal numerical model to simulate a number of extreme storm events and evaluate whether we can actually obtain accurate and reliable estimates of storm-induced subaerial erosion using synthetic and representative bathymetries. So for this study, two contrasting sites were chosen. On the left, we've got Narrabeen Collaroy, which is an embayed beach uh, in New South Wales, Australia. And on the right, we've got Duck, which is an alongshore uniform barrier island on the east coast of the USA. And these two sites were chosen because a number of pre-storm and post-storm topography and bathymetry surveys are available at these sites through long-term monitoring programs. From the data available, a total of 12 storm events were chosen to be modeled for this study, 7 at Narrabeen, Collaroy, and 5 at Duck. The modeling was carried out along a cross-shore transect located within the study site, and the XBeach model was forced with measured waves from offshore wave buoys and water levels from tide gauges. For the modeling process, 6 bathymetry scenarios were created. So firstly, a pre-storm surveyed bathymetry for whichever storms where this dataset was available. An upper bathymetry, which was created from the upper 95% confidence interval of all bathy surveys carried out at a site. An average bathymetry, which is the average of all bathy surveys at a site. A lower bathymetry, which is the lower 95% confidence interval of all bathy surveys at a site. An equilibrium type profile where the equation of the profile is defined by Dean is given by this equation here, where the water depth h at a given distance x from the shoreline is given as a function of a constant m and a scale factor a. The scale factor can be calculated by knowing the cross-shore location of a given contour. So for this profile, I've chosen the 5-meter contour so that the profile passes through the shoreline, the 0, 0, and then the minus 5-meter contour. And I'll refer to that as Dean 5. A second equilibrium profile was also created, and this time the A factor, the scale factor, was calculated based on the 10-meter contour. So this time the profile passes through the 0-meter contour and the minus 10-meter contour at both sites. And I'll refer to that as Dean 10. So every storm event that was selected in this study was modeled using each of the bathymetry scenarios that I just described. So initially, XBeach is calibrated with a given bathymetry scenario, and the same bathymetry that's used for the calibration is used to model the storm event. So if we take an example of a single storm event, we carry out a rigorous calibration process using the pre-storm surveyed bathy, and we get a set of optimal parameter values which are unique to having used that pre-storm surveyed bathy in the calibration process. We then model storm event 1, providing the pre-storm surveyed bathy as the input to the storm with the measured waves and water levels, and we get an erosion estimate. If we do the same thing using the average bathymetry, so provide the average bathymetry as input to the calibration storms, we carry out the calibration process and we get a set of optimal parameter values which are unique to having used that average bathymetry and which are different to what we obtain when we use the pre-storm surveyed bathy. We then model storm event 1 using that average bathymetry as an input with the measured waves and water levels, and we get another erosion estimate. We do the same for all 6 bathymetry scenarios and we get a set of erosion estimates for all 6 bathy scenarios. And because we've used the measured waves and the measured water levels, the same pre-storm topography for the modeling process, any variation which we observe in these erosion estimates would only be a function of the bathymetry which we've used throughout the process. So by comparing these erosion estimates to the actual observed erosion during that storm event, we can evaluate how accurate and reliable these erosion estimates are. And from that, we come up with a conclusion on whether we can obtain reliable estimates using these bathymetry scenarios. So this figure here shows the variation in So this figure here shows the variation in optimal parameter values for XBeach as a function of the bathymetry which we've used to calibrate the model. So on top we've got narrowbeam and on the bottom we've got duck. The 4 parameters which were selected for calibration at each of these sites were determined by carrying out an initial general sensitivity analysis to reduce the number of parameters which needed to be selected for the optimization process, and also to minimize the parameter space which needed to be used for the calibration. So which is the gray area highlighted here in each of the parameters. And what we notice is that at both sites, the parameter which has the greatest influence on model output, which is the 2 Facua parameters, they adjust based on the bathymetry which we've used for the calibration. So the model accounts for the differences in these bathymetry scenarios by adjusting these parameters. And the results of this adjustment become quite clear once we start looking at the erosion estimates. So this figure shows the subaerial erosion at narrowbeam on top and for duck on the bottom here. On the x-axis, we've got the observed subaerial erosion, and on the y-axis, we've got the modeled subaerial erosion, which in this case is the model output when we use the pre-storm surveyed bathy. So for narrowbeam, only the calibration storms are shown because even though there are quite a few surveyed bathymetries at the site, only 3 could be classified as pre-storm surveys. And in this study, we've made a clear distinction between just surveyed bathymetry and pre-storm surveyed bathy. But even with that being the case, we can see that at narrowbeam, the XBeach has quite a good skill in predicting the subaerial erosion, but it doesn't seem to be the case with duck. What I'll also point out is that the scale at narrowbeam and duck is quite different. So even though all the storm events that we modeled at duck, except one event, were all named hurricanes, the amount of subaerial erosion which we observe at duck is minimal compared to what we observe at narrowbeam. So because the morphodynamic response of these two study sites is quite different to the storm events. So even with that being the case, though, we see that XBeach is able to predict the magnitude approximately correctly and doesn't significantly overestimate the erosion. If we then compare these model outputs to the output we would have observed if we had used the average of the Dean profiles, we see that even though these 2 sites have quite a different morphodynamic response to storm events, using the average bathymetry results in erosion estimates which are similar to what we would have obtained if we had used the pre-storm surveyed bathy. Similarly, for the Dean profiles, for storm events where there's more subaerial erosion, the Dean profiles result in erosion estimates which are similar to what we would have obtained if we had used the pre-storm surveyed bathy. But they do tend to overestimate the erosion for smaller erosion events, and the Dean 10 tends to do that more than the Dean 5 profile. With the lower and the upper bathy, though, we see that the lower bathy doesn't have any skill in predicting subaerial erosion at either side, whereas the upper bathy at narrowbeam over predicts the erosion, but at duck, it predicts the magnitude quite accurately. And the reason for this lack of skill in the lower bathymetry and the inconsistency between sites in the upper bathy is because the upper and the lower bathys represent extreme conditions of the subaerial beach. So extremely accreted or extremely eroded subaerial beach conditions. which might not necessarily be consistent what we would observe during for the pre-storm survey topography. So when we try and combine the pre-storm survey topography with the upper or the lower bathy, we end up with surf zone characteristics which we generally wouldn't observe at a site, and also we see quite significant variations as the in the morphology which we create, because the pre-storm topography would change between storm events. So with this study, what we aimed to do was to evaluate the degree to which we could obtain reliable representative bathies. And what we were able to identify was that we don't necessarily need pre-storm surveyed bathy to carry out operational forecasting, but we can use synthetic and representative bathymetries and get erosion estimates similar to what we would have obtained if we had used the pre-storm surveyed bathy, as long as the XBeach model is properly calibrated. So for a given site, the way we want to carry out erosion forecasting, if multiple bathymetry surveys are available, then we can use an average bathymetry and get reliable estimates of subaerial erosion for storms of varying magnitudes. But if a site doesn't have any data available, as long as we know the location of certain contours, the -5 meter contour and the -10 meter contour, we can use an equilibrium type profile and again still be able to get reliable estimates of subaerial erosion for storm events where there's more erosion. So, but we have to keep in mind that using the equilibrium profiles might overestimate erosion for smaller events. But the results of this study also suggest that using a prior surveyed bathymetry that's not a pre-storm survey might not result in reliable erosion predictions, because we wouldn't have an idea of where that prior surveyed bathymetry lay within the envelope of variability which we expect at a site. So by using that prior surveyed bathy, we might end up with a lower bathy which would have no skill in predicting the subaerial erosion, or we might end up with an upper bathy, in which case we'd have to carry out further analysis to see whether it can provide reliable estimates for that given study site. Thank you. I'm more than happy to answer any questions you have.